Lesson 1 is on the derivative. At the end of this lesson, the student must be able to differentiate a function using the definition of the derivative, or a method known as the four-step rule method or the increment method. In differential calculus, we will be making use of a process of finding the derivative of a function, and this process is known as differentiation. That given a function, we differentiate it to obtain its derivative. Now, differentiation is an important mathematical tool in physics, mechanics, economics, and other disciplines that involve change and motion. The derivative of a function is given as follows. The derivative of y, the f function of x, at point P on the curve is equal to the slope of the tangent line at P. Thus, the derivative of the function f given by y is equal to the f function of x with respect to x at any x value in its domain is defined as follows. It is the limit of delta y divided by delta x as delta x approaches 0, or it is the limit of the difference of f of x plus delta x minus f of x divided by delta x as delta x approaches 0. The derivative of y with respect to x is denoted by the symbol read as dy dx, or the derivative of y with respect to x. This is how we define the derivative, provided that the limit exists. We can follow this definition of the derivative by making use of this illustration. Consider the graph of the function given by the blue curve. This is the graph of y equal to f of x. Now take 2 points on this graph given by P with coordinates x sub 1 f of x1 and Q with coordinates x sub 2 f of x sub 2. Joining P to Q will give us a line that is known as a secant line, the slope of which is given by delta y divided by delta x. Delta y is just the increment or the increase in y value as you move from P to Q, and delta x is the increase or the increment in x value also going from P to Q. Now let us move Q along the curve of y equal to f of x, moving it closer and closer to P. As we move Q closer to P, the secant line tends to rotate. So if this is where Q is, the secant line would be going this way. If Q is over here, then the secant line is oriented that way. So as you can see, the secant line tends to rotate, pivoting about the point P, and that the secant line tends to move closer and closer to this line, which is the tangent line to the curve at P. It is on this basis that the limit of delta y divided by delta x, which is the slope of the secant line, as we move Q closer and closer to P, making delta x to approach 0, to be the slope of the tangent line at point P. So the derivative of y with respect to x will just give us the slope of the tangent line to the curve at point P, provided that this limit exists. Recall how we define the derivative of a function dy dx. It is defined in terms of the limit of the ratio delta y divided by delta x as delta x approaches 0, or we have it in terms of the limit of the difference of f of x plus delta x minus f of x divided by delta x as delta x approaches 0. In this definition of the derivative of y with respect to x, we have here ratio of the increments in yn and in x. Or that in the process of working out the derivative of y with respect to x on the basis of this definition, we will be required to do the following. First is to define f of x plus delta x, and then work on the difference before we divide that difference by delta x, and finally determine the limit as delta x approaches 0. Because of this, we come up with a method of determining the derivative of the function y with respect to x, and this is called the increment method because we made use of increments, or we have the four-step rule because in the process of determining the derivative of a function y with respect to x, we do the following steps. First is that we substitute x plus delta x for x in this expression. So that is defining now f of x plus delta x. And in the process, we substitute y plus delta y for y in that form of the function y equal to f of x. The second step is to subtract y, which is f of x, from the result of step 1. So in the process, we are now doing this difference. And then the next step is to divide whatever is this difference by delta x. So divide both sides of step 2 by delta x, and then finally find the limit of step 3 as delta x approaches 0. So as you can see, if you will be working on the derivative of the function based on the definition, you will be doing or following basically 4 steps. To illustrate how the method works, let us find the derivative dy dx using the 4-step rule given y to equal 2 plus x squared. The first step is to define y plus delta y given by 2 plus the square of x plus delta x. This was obtained by replacing that x with x plus delta x. The second step is to define the difference between y plus delta y and y given by the difference between 2 plus the square of x plus delta x and y. So that the difference y plus delta y minus y would just be equal to delta y, and on the right we will have 2 plus the square of x plus delta x given by x squared plus 2x delta x plus delta x squared minus y given by the sum 2 plus x squared. Or we will have 2 plus x squared plus 2x delta x plus delta x squared minus 2 minus x squared defining delta y. So that when we simplify delta y, noting that 2 minus 2 is 0 and x squared minus x squared is 0, then delta y will just equal the sum 2x delta x plus the square of delta x. Or we have this given by the product between delta x and the sum 2x plus delta x. Now please take note that x and delta x are two different variables. Moving on and doing step 3, obtaining the ratio of delta y to delta x, dividing the product delta y times 2x plus delta x by delta x will just result to the ratio delta y divided by delta x given by 2x plus delta x. Again, take note that x and delta x are two different variables. So that if we will be working on the limit of delta y divided by delta x as delta x approaches 0, it is just the delta x variable that will be getting closer and closer to 0, but not x. so that for this sum of 2x plus delta x, as delta x approaches 0, it is the term delta x that will be approaching 0, and therefore the limit of this expression would just be equal to 2x. It is on this basis that we now conclude the derivative of y with respect to x, or the derivative of 2 plus x squared with respect to x would just be equal to 2x. Summarizing what we have in this lesson, that the derivative of a function f of x with respect to its independent variable x, denoted by the symbol dy dx, is defined as follows: that it is just the limit of delta y divided by delta x as delta x approaches 0, or we have it equal to the limit of the difference between f of x plus delta x and f of x divided by delta x as delta x approaches 0, provided that this limit exists, and that geometrically the derivative dy dx is interpreted as the slope of the tangent line to the curve of f of x at a given point P.